at the time. So welcome everybody to this installment of the OMFIT tutorials. We have Oak Nelson here today to talk to us about the OMFIT profiles module. Oak is a graduate of Colorado and then Princeton, and he's currently a scientist at Columbia. He said he spent all of his thesis working on the OMFIT profiles module. So expect good things. Thank you, Oak.
Thanks, Sterling. Yeah, so we're here to talk about, I think, one of the most fundamental parts of tokamak analysis, which is somehow mapping things to radial coordinates and somehow getting information about the inside of your plasma. Often these are profiles of temperature, or density, or et cetera. And you can see in this project that I've already pulled up a bunch of different GUIs. OMFIT profiles at the top, which is what we'll talk about today, is not your only option when fitting profiles in OMFIT. And there's even options outside of OMFIT as well. A lot of these are specific to other workflows. There's a GA profiles module, which has been OMFITized. Tom Osborne has whole profit routine, which is also OMFITized. Zip fits are done automatically. And so they're of lower fidelity, but really fast. You can get them in OMFIT. Quick fit is a really nice tool that Tomasz Odrzycil developed. And he'll be back in a future installment of this tutorial to talk more about that in depth. And then profiles gen GA code is a very useful thing for making profiles for all the GA code suites like CGyro, JGLF, et cetera. I think OMFIT profiles is probably the most intro friendly in that it very obviously is doing what it does. And you still have a lot of control over what you're getting. But each one of these has their own strengths and weaknesses. So do feel free to explore them if you want. I also really wanted to highlight OMFIT profiles is a very well-developed module, and it has some great tutorials already online. So today we're going to try to talk about stuff that's not already in those tutorials. So if you want to go through just like a step-by-step workflow, you can go to omfit.io, which is OMFIT's homepage. And then on the modules, there's a bunch of different lists. In here is OMFIT profiles, which will bring you to this page. Long description, typical workflows, support devices, several different forms of tutorials, both for D3D and K-star. And you can see just by list of contributors that quite a few people have contributed to this module as well. This is a great example of OMFIT being completely open source, right? There are several people that did a lot of programming, but then there's a lot of other people that have added a function or added a plotting thing or something like that. And so this is a great example of that all coming to fruition. So if you open up the OMFIT profiles PDF tutorial, this guy here, you'll get brought to this page, which gives you some introduction about the module and walks you through eventually a D3D example showing you some basic stuff. I wanted to just highlight two parts of this tutorial before going into a working example. The first is, I guess that being that there are two distinct workflows available within this module. Maybe I can make the zooming on this a little bit better for people. Where's the zoom button? Zoom, zoom, zoom. There you go. So there's two different workflows, which we'll see. There's a 1D workflow, which you can interact with. And this is basically the original OMFIT profiles workflow. It lets you do everything on a common time basis. It takes slices of information for particular shots. It's described a little bit more in depth here. And then there's a 2D workflow, which is essentially identical, except for it forgets slicing and allows you to instead fit with time constraints as well. So this introduces 2D fitting. So you can smooth stuff out over time if you think that there's one like extraneous event or something like that, or have previous steps in form fitting for other steps, which drastically helps to speed up the process. So the big advantage of a 2D workflow is that it'll go a lot faster if you're doing lots of time slices. For this tutorial, we're going to do just a few time slices because it's simple, and thus we're going to use the 1D workflow. Cool. So I've loaded an OMFIT profiles module here. Again, this is done just by file, import module, and then you can select OMFIT profiles and import it. And when you open it up, it will look something, I think it actually defaults to the 2D fitting now. So it'll look something like this. This is a complicated module. It has lots of different tabs. But they all are wrapped in one really nice wrapper: fetch plus map plus slice plus fit. And this is basically instructions for what you do in the module. If you press this button, which I'll do and I'll keep talking, it'll go through every step that you want OMFIT profiles to go through, and it'll do them automatically with default settings. And at the end of it, it will give you profiles. So one button, do it all. What is it actually doing here? Well, it's fetching the data. It's mapping those to an equilibrium, because we have to know how to transfer between physical space from the diagnostic into our equilibrium space with normalized axis. We're slicing it because this is a 1D time slice workflow. So we're taking everything around a particular bin in time and putting that together and averaging over that. And then we're fitting it with some fit. And each one of these steps, you can see in these tabs, which we'll walk through in a second, has lots of sub-steps that you can iterate on, lots of details that you can add in and take out, and lots of assumptions that you can apply as well. But the general basic workflow is just press the button and go. Yeah.
When you uncheck the 4 check marks you have in the under main, does that make your wrapper have the unchecked one now not execute?
That's exactly right. Yeah. So if you uncheck one of these buttons, it'll take off the stage from this full thing. So for example, if you already fetched the data, fetching the data takes a while. So you can undo that, right? Or if you're running the 2D workflow, you don't want to slice the data, fine. Or if you know you're going to have to do some manual fitting, you can uncheck the fitting, so you just don't saves yourself some time there. It's actually pretty cool. This is a neat little GUI, because the buttons will impact, or the check marks here impact what the button says. So it's very obvious. And so if you want to do fancy GUI stuff in development, you can check out how that was written and see how it goes. So we're almost done. We're fitting now. Sweet. So that's how long it took to run 3 time slices for this particular shot, which is just a random shot I worked on in the past. And now that it's done, we can go to this plot tab and we can look at what our profiles would look like. So this plot tab brings up a ton of different options. You can plot raw signals. You can choose different fits to plot. You can plot derived signals, which we'll talk about in a bit. And then different ways to do that: plot in 2D, plot in 1D. I'm just going to choose a simple option, plot 1D static profiles, to show you guys that this did do something. Here are a bunch of profiles. We have electron density, we have electron temperature, we have the emissivity, carbon data, and then there's other spaces for other things if we want to fit them or calculate derive down below. I have 3 time slices here, right? 1,000, 2,500, and 4,000. And each one of these is fit, and you can see little dots here which correspond to the sliced points that we're fitting through. So we can look at this and we can debate if it's well fit or not. I mean, it looks fairly decent, right? I mean, just from a bird's eye view, the lines go through the points. There are, if we zoom in on the pedestal, hopefully that works.
Change tabs with new cycle. Yeah.
Okay, cool. Yeah, so if we try to like zoom in on the pedestal here, I mean, we can see we're doing a decent job. Maybe this density, the fit is not quite as steep as the dots. You could argue by eye, right? So maybe we want to tweak that a bit. I also noticed, looking at this whole view, that for these 2 later time points, 25,000 and 4,000, the CER data, both for the temperature and the density, stops here, right? So we don't actually have any constraints in the core, which is a bit of an issue, right? We don't know anything about the core data here. So we can talk about maybe how to mitigate that based on external stuff as well. So yeah, I just want to highlight simply pressing the button works, and that's a great way forward. But there's a lot of other options in here that we can explore. So let's see, kind of, I think maybe the most intuitive way to do this might be to work backwards, because we have our real result, and these are just options that go into them. So we'll kind of bounce around a bit. But of course, this is a fitting tool. So maybe the most interesting tab for a lot of people is the fitting tab. So if you go to the fitting tab here, you can see we have a ton of options, right? This is the default that OMFIT profiles opens up with. It's using radial basis functions. It has some spaces as a row. If we don't know what these mean, we can click the question mark boxes. Most things in OMFIT profiles are really well documented. So this, for example, is telling us that it's giving different fit methods that may be appropriate for different characteristics of data, different applications of interest. This is absolutely true, right? Sometimes you're really careful about the edge fit. Sometimes you want to know about the core fit. Sometimes you're applying some particular fit that you've developed. For this radial basis functions fit, there's information about what these are. And so we could play around with these. So let's say we go to the electron density, right? Because each one of these lets us fit different settings for each one of the profiles. Right now, this looks like this, right? We have some fit, and if I press the forward arrow or back arrow, it'll go forward or back in time. So this is a fit a little later, fit a little later. It doesn't look that bad, right? For a lot of purposes, this fit is going to be great. I mentioned earlier that maybe the pedestal isn't quite right, and we can see that again looking at the data here. We have a fit through the pedestal, right? But it's not quite as steep as the data would suggest. And so if I'm trying to do something that really depends on the pedestal, like an EPED type analysis, this sort of fit might be skewing that data. So I have some options, right? Just looking at this radial basis function here, it gives me some fitting parameters that I can change here. It also lets me apply bases in row. So I can say, okay, I want more bases in row. There's a space-time correlation ratio, which relates the factor you're changing in space versus time. This is especially important for the 2D fits. We won't touch it here, but do play around with it. There's also an additional edge bias. So if I want to increase that, say I can set it to 5, we'll fit and plot again. From the bird's eye view, it doesn't look like much changed. Maybe it's a little smoother actually. If we zoom in on the pedestal, maybe we're capturing the bottom here a little bit better, right? But we're still not really capturing this peak at the top. So this didn't help us get towards something that we want, but it's not all the way there already. And you can play around with this more, of course. But what I really want to highlight is that there's different fitting methods as well. And so just clicking this opens up a drop-down menu with lots of different ways you can fit. And these are actually completely addable as well. If you have a new method that you want to put in here that's not here, you can absolutely put it in and push it to the tree and share it with everybody. A really common one on D3D is core polynomial and edge exponential MTNH blend. So this comes to the standard fits to the H mode pedestal that we know about that use an MTNH fitting. So if I click this, you'll see the GUI changes. I have a lot more different options now. Move my zoom bar around. And so this has a core polynomial, some order in the center. And it also has an edge exponential, so tan H at the edge, and then it smooths the two together. And so let's just try these default fittings and see what happens. You'll see, or maybe you didn't notice this earlier, but the radial basis functions came with like an extra blue shade around these. Those will calculate uncertainty for you. The core tan H one doesn't, right? So by moving to this different fitting method, we're getting rid of automatic uncertainties in the OMFIT profiles GUI, but we're maybe gaining a better fit, right? So this looks pretty good, looks pretty smooth. If we zoom in on our pedestal now, we can see we're really much better able to capture all the way that pedestal height, right? We're getting up to the top, we're following the same gradient all the way down, and we're capturing the bottom quite well. So this seems to be doing a little bit better in the edge than the radial basis functions defaults, right? I mean, you can play around with other data sets to see how that goes. No, this was the default case, right? I chose this case because it's a very typical D3D H mode, but not all your cases are going to be very typical D3D H modes, right? There's still a lot of options within this case. For example, like we could increase our core polynomial over to 5, and we could get rid of a constraint to have 0 on axis and see what that does, right? It looks okay, except for now our core is kind of blowing up, right? So we're fitting, compared to the 2 core polynomial now, we're fitting our curves in the core a lot better, but we're blowing up at the axis, right? So maybe turning off the axis constraint was a bad idea. We can put that back in. And go look at what we have here. I mean, so now we're kind of fitting this, but we're not really fitting the curve of the data. If you wanted to go into like really overfitting, I think this lets you get up to 10. I wouldn't recommend that. I like to stay in like the 3 to 4 range for your core polynomial. Much more than that, and you can start just getting a ton of wobbles that maybe we don't believe, right? So this is not necessarily good, but something I usually use something like 3 to 4. But again, this just depends on your data. There will also be cases when you have a pedestal that is not right in these default H mode parameters, right? So we can change where we think that pedestal is and move it in, move it out, move it wide. We can give it a minimum width, and so you can use that. Especially this is impactful in like the NT discharges, where the pedestal looks very different than in H mode discharge. And so I've been using these pedestal constraints to kind of force the fit to do what I want in the edge, and get a better fit of the data that way. So let's talk about one of those problems we had. So if you remember, we didn't have CER data in the core. So if we're looking at our core time slices, this is time slice 1, it looks pretty fine. This is time slice 2, and this is time slice 3, right? We literally, the fit is completely unconstrained here using the radial basis functions. So there's many ways around this, right? I mean, really easy way around it would be to put a linear fit and just fit a line. I think we can guess that that's probably not going to look very good. If we use something like the core tan H here, what happens? How does it respond to missing a bunch of data in the core? For the first one where there is data, it looks okay. For the second one, you can see that the core tan H has a little bit more just emphasis on keeping it flat there, right? This is just a natural fit. But it also has abilities to fit core value, right? So if I had some reason, say I know that the core value is a particular, let's do this in temperature, for example. So going to the temperatures, which had the same problem. The temperature brings up another interesting condition about the edge, which is why I want to switch here. So we have some peaking, right, with our core temperature that was just randomly guessed by the discharge. But you can see between these two different times, which I'll tell you, there's no difference between these two different times in the experiment. It was a steady state discharge with nothing changing between 2.5 and 4 seconds. The core peaking changes a lot, right, just with our manual fit. So say we don't like that, and we are smarter than the machine, and we know some value which we could constrain the on-axis, say like 5 keV, right? So I can put in a constraint like that, and now when I fit it, we should get, so this is obviously not good for time-dependent analysis because this first case doesn't have a 5 keV core, right? But now these later two cases are not jumping around a bunch, right? And so this is just, it's iterative. You have to be really careful with it and look where you're going. So the core, or the ion temperature in D3D is a tricky one, especially at the edge, right? You can see these CER measurements at the edge jump up quite a bit, right, at separatrix, and they stay high all the way through the scrape-off layer. So if I try to use any sort of fit, we can go back to the radial basis functions fit here. That's the data it has. That's the data it's pulling from the machine. And so it's going to try and fit that at the edge. And depending on what code you're running, this may or may not be an issue, right? So depending on your purposes, maybe we want to say, okay, well, I don't actually trust that the ion temperature is 1,000,000 degrees, right, at separatrix, right? This is a known issue. Maybe I can get around it. And so the question now becomes, okay, how can I deal with that within the OMFIT profiles GUI framework? And that brings us to another tab. So working backwards still. Yeah, question.
Question in the chat.
Oh, question in the chat. Yes, thank you. We have a question. Would you say it's a good idea to change the fitting method depending on which region of the plasma is your priority? And yes, I think this can absolutely be a good idea. There are reasons to use some and reasons to use others. Typically, you want to play around and see not only which region is your priority, but what influences of the profiles will affect modeling you run down the line, right? So if I'm running like transport modeling or stability modeling, certain aspects of my profile can really influence those results. And so I want to make sure those certain aspects of those profiles are captured well, and maybe other things aren't as important. Radial basis functions is like a really default option, right? But there's other things in here. There's two versions that combine with the M10H. There's typical spline features, which are really similar to GA profiles, which are used in a lot of cases, especially equilibrium fitting. So if you're working with some equilibrium codes, that can be a good option. There's just using gradient scale links, et cetera, which can be useful for transport and turbulence and analysis in that manner. Yeah, so I mean, I won't go through each and every one of these, but each of these fitting does serve a purpose, and it's here for a reason. Someone thought it was important, right? And so probably they all have some use. Great, yeah. Thanks for the question. Yeah. Yeah.
Does the help apply to, like, to describe each of those fitting functions?
Yeah, so this question mark, I don't think explains each one, but I believe they're covered in, well, at least some of them are covered in the online tutorial in terms of what they do. But if you open one up, I mean, you can play around with it just for a sec to see what it does. And these helps will tell you about what each of the parameters is. And I think that's pretty well documented, so that the individual parameters for the fit are right here in the GUI. The fits themselves, yeah, I guess you kind of have to know what they do, or check the source code, because I think there's a lot of comments in there as well. Cool. So we were at fit, and we were here. We were trying to figure out what to do with the ion temperature, because the D3D ion temperature at the edge is sometimes crazy, right? This is obviously not the typical H mode thing we're used to seeing. So now we get into the danger zone where you're making decisions to override data, right? Because we have data and it says it goes up. And so we're making a mental decision now to say, okay, we have a reason to not trust this for a particular thing or what. And there's lots of ways to influence this going forward. The first way is this select tab. So if I go back a bit, and I mean, you can just show, oh, shouldn't have dragged. If you show the diagnostics, right, you can get a feel for where these are all located. One thing that can particularly happen in a lot of D3D cases, which I guess we'll go to, well, I'll skip that. I'll come back to that. But the CER, the CER channels do span the edge region, but they span the edge region based on these different suffixes at the end of your CER data. And there's also tangential and vertical channels. The suffixes refer to which beam, the beamline you're using to take the data. So these are my two controls for CER data, right? The select tab is going to let me select different data to include or data to exclude. So if I go to Tang, which is a tangential, and I just select one of these subsystems, you can see already it gives me options to include data from this in temperature, or separately in density, or separately in rotation, right? So I don't have to do the same thing for each channel that I'm trying to fit. And I think this is already default set for vertical channels to not be included for anything except for the density, which is typically a good idea. The tangential channel also has some little warnings here when you look at it. It says, may be more accurate than vert due to spatial averaging. So that's why it's used in temperature and not in the vertical channels. It also gives you a warning, low voltage beams are less accurate, which is something we'll talk about in a little second. But to get a feel of what's going on in my discharge, I can plot all of this data as a slice tab, right? And that gets me this, which I would love to make bigger. Hopefully it doesn't disappear on me. There we go. So this is all the data we have for temperature, rotation, and density from these channels. And you can see that, yeah, again, a lot of the edge channels here are quite high. A really common way to remove these from your fit, if you will, I can go in and I can click on one of these points, say this point, and it'll tell me what channel this is coming from. This is T44 from 33R. This one is T46 from 33. All right. And so if I go back to the GUI and I find 33R, the beamline, and then I go and find T44, was it? and T46. We'll turn off T45 in the middle too, just for visual effect. If I replot this, we'll see if I got the right ones or not. Now those particular cases are grayed out. So zooming in for visibility, right? These were the cases I was just looking at. And they're gray, which means they're no longer selected as active channels when I'm doing a fit. So if I go back now to my fit and I choose ion temperature, and we come back here and we try to fit and plot 1D, we're no longer going to be fitting the points right at the edge here. We're still fitting the scrape off layer, so it's still bumping up, but I can change that, get rid of the fit scrape off layer. Now you can see we're not really fitting that. This first one still goes up quite a bit because of these two channels which we left in. These ones, those two channels are right here. The up channels, right, the separatrix are gone now. This one looks like it's almost falling down, right? Again, we're kind of fudging stuff here, right? We're saying this probably looks a little bit more realistic than it used to look, but we're still probably making something up. We can fudge it even further if we want to. We could add an edge value constraint and say, hey, I want everything to be 80 EV at the edge, and then plot that way, right? And this is just an example of one way to kind of work your way around different fits in the OMFIT profiles GUI. So here, oops.
Like inside the axis.
This works. So here, again, we kind of give up on this fit, but now both of these cases we're forcing some edge temperature constraint, right? Which we could inform through some theory or some model, and try to get a better value of what this ion temperature pedestal should be. The tools are there for you to do with them. If you do want to take advantage of these tools, I highly, 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 highly recommend talking to a CER expert, and they'll help you work through this in a way that makes physical sense. Don't just go and edit your fits and ignore data at will. Please be responsible. But the tools are there for you to capture the physics that you need. Speaking of editing data at will, there's another option in CER, which is low voltage beams are less accurate. So if you go down to this advanced setting, you can open a control panel, which gives you the opportunity to have correction factors for each of your beams. Why might you want to do this is a good question. Let's see if we have an example. We don't really have a good example in this discharge because this discharge works well. But you'll see in other discharges, no doubt, if you analyze them, one CER channel from one beam might be here, and then suddenly you'll have a different beam that starts right here, which is giving you a measurement up here. Or you'll have a different beam down here that's giving you a measurement there. And so you'll have conflicting measurements for a particular location in the plasma, which of course is somehow unphysical. And so this advanced panel gives you a chance to correct for that. So you can scale different versions depending on their beams. Typically, we like to scale to the one with the highest voltage because that's the most accurate. If you press this show background information on the CER console, it'll print something for you, which is very important. It prints information. Why does this happen? Ideally, you should ask the CER experts for help. They will help you. This is the best way forward. At a last resort, you can do stuff yourself, and this is maybe some stuff to do. But that's just, I won't go through this because you should definitely go through it with an expert manually in case-by-case basis. But if you do encounter this issue where CER seems to be like not perfectly uniform across the whole plasma, there are ways to deal with that as well. Similar things apply to Thomson scattering. There's like one point that you think is like, oh, this is somehow an outlier and it's messing up my fit. So you can just remove that point from your analysis, or you can talk to the Thomson team, see why that point seems to be an outlier, and et cetera, et cetera. So there's options to select which diagnostics you're using in the select tab. Great. We've covered select and we've covered fit. Let's go to post-fit because that seems finicky. So post-fit, what does this do? If you remember back in the derived category, or sorry, in this plot category, there's this option for derived. And this is actually one of the most useful things about OMFIT profiles, in my opinion. If you go to the outputs tree, in addition to the fits, which are just the parameters that we have actual data for, there is a derived, which is a lot of different parameters that we're not explicitly measuring. For example, I don't know, the thermal pressure, right? This is a pretty important parameter for a lot of analysis, but it's not directly measured in any profile fitting stuff. This is all done with a script. When you can see the scripts here are nicely labeled. There's a ton of them in the OMFIT tree, but the main ones here: fetch, timings, channels, post slice. Post slice is the one that does most of the derived. So if you want to know how it's doing some calculation for some fancy parameter, you can look in there. The derived tab itself looks like this, right? So by default, it just has electric field quantities turned on. If you look in your derived category and you look for ER, you'll notice that we have some of the typical ER terms, but not all of them. This relates to the V pole, which is an entry into the ER calculation, which is off by default. You have two options. Either you can go and turn it on in your select tree, or you can say, okay, I'm just going to set V pole equal to 0 and do an ER calculation, which is typically okay for like a first level analysis in D3D. You can also calculate additional gradients and scalings. You can calculate pedestal width and height parameters. And then all of this gets you back to running the derived tree. So now if we run this again, you can see it will update with a lot more. Now we have a lot more gradients in here. We have information about where is the pedestal inside, where is the pedestal outside, which is good for pedestal studies. And we have a lot more ER options, including just the electric field itself, right, which includes all these different terms, the grad P term, the V pole term, and the V toroidal term right here. So great. And it also did that for the main ion species, which was not directly measured in the shot. We only had carbon species. So a lot of extra information that we can get from these fits just by standard application, right? And now if I go to the plot tree, these will be available in my derived plots. I can scroll down and I can find the ER well, and I can go and plot this as a static profile. And now it will show up in the bottom. Maybe, yeah, so here's my ER well for these shots, right? And because we actually already went through and made something of a decent ion temperature pedestal, it looks like these ER wells are fairly normal, HMO-like. If you have weird ion temperature on the edge, your ER calculation might be looking odd. Sweet. So that's one of the tabs in post-fit. That's the most obvious. There's also controls here for TS separatrix, CER NIMP, and CER separatrix. What are these? If you get really into fitting of profiles in D3D, especially fitting in the edge, there are many times where you'll be looking at your edge and you say, this is not consistent with the typical expectations for D3D, et cetera. And so this allows you to actually shift your profiles back and forth radially and better align your profiles with what you expect the temperature to be. Why might we want to do this? So I'd come back to this plot. Here's the plot again. Never make anything bigger. The diagnostics are, of course, mapped here onto this 2D grid, right? And what that grid looks like, what the equilibrium reconstruction is very important into how this works. That's the subject of the next tutorial, so definitely come back for that one. But we thought it's good to color profiles first. This is a 2D grid of a 3D machine in a very complicated geometry, right? And there can be slight 3D effects in this that will offset some 2D calculations at various colloidal locations around the tokamak, right? And so that can give you slight shifts in your diagnostic rotations on the order of millimeters, right? But millimeters can impact your edge constraints. So, for example, let's look at the Thompson. A typical value for TE at the edge in D3D is something like 80 EV. This comes from large database studies, right? And of course, set this value if you want to fit it to something else because it's an input. But what this will do is it'll go through and say, okay, where in my discharge is it actually 80 EV? and it will tell you how close your fit is to being good from that parameter space. So you can see, I mean, these are pretty decent, right? I'm only fitting these on a base equilibrium EFIT of 1, but they're already pretty good. If I fit them on a better equilibrium, maybe I'd get a better agreement here. The other option is to apply some separatrix workflow here to shift them directly in OMFIT profiles. So there's 3 workflows. There's form constraint for EFITs, which is related to EFIT reconstruction, which we'll talk about in 2 weeks. And then there's shift diagnostics and stretch fit, both of which have the effect of doing what they say. So shift diagnostics and OMFIT profiles will move the diagnostics over slightly so that your profile will agree with what you wanted it to be. Stretch fit, we can demonstrate, will stretch your fits. So if I apply this workflow, and then I recalculate the derived quantities, which I should probably turn some of them off so it takes a little shorter. If we go and so this is going through and updating all of our fits and all of our derived quantities. If we go through and plot it again, we can now see that all of our temperature pedestals and separatrix are exactly aligned with what we told them to be aligned with, right? And this is, I mean, some way to get alignment. A keen observer would have noticed that when I did this automatic alignment, I was forcing everything to the same position, right? Whereas, didn't quite reset all the way. That's okay. So these initial values were slightly different for each time slice, right? And it's up to you as a physicist how to interpret that, right? If you have some plasma that's dynamically changing over time, maybe that's okay. If you have a single plasma that's sitting there all the time, and you still have some variation how much you're shifting it, maybe that's a sign that you shouldn't be forcing everything to 80, right? Maybe you should take like the average value of those shifts and shift them all by an equal amount or something like that. And then you'll still have some slight variation in your separatrix temperature and density, but you'll be more on par with like the D3D standards. Similar things can be applied in these 2 tabs. We won't walk through them all because there's just a million details. This lets you calculate the impurity density directly from the CR density, and has some different opportunities to do that. CR separatrix, it's basically the same thing as TS separatrix. It gives you the options either to fit the density in carbon with respect to the density in the electrons. So this is showing, okay, if I wanted my ion and electron densities to match up, how much would I have to shift my ion profiles to make that happen? Is that a good amount? Is that not? This is quite a big shift. And so, I don't know, we'd have to think about that one. It also lets you do another fit in the edge, which is to your ER well. The ER well should have a dip and then come back up through 0 right around the separatrix. So if we have our ER calculation turned on well, we can see where that dip is currently calculated. It's a little bit inside. I could adjust that. This is not quite as big of a shift. Maybe I would go with this one. And then you have to recalculate derived and an iterative process back and forth to figure out exactly how your ER lines up. So there's definitely more room for manual analysis in this tab as well. Cool. Any questions on any of this so far? Yeah.
You mentioned this, I don't know, hypothetical option that we could just shift everything with like all the profiles in the shot with the same radial mount. Is that something which is implemented here?
So that button currently doesn't exist, but this is a great example of how to do something manually, which I was hoping to cover. So this is a good segue. Say we have, let's just refit everything. Where's our temperature? We have temperature. So say we have our temperature profiles and they don't line up, right? So we have some different values here, but we think, hey, well, I can tell you for this shot, this is not a good idea, right? Because we know that 1000 is very different from 25 and 4. We already kind of saw that in the profiles they're showing. But say we thought all these were going to be the same, right? How would we make these all 3 the same? If I right click on this box, right, which is just a list of my shifts for each time point, it'll tell me where in the GUI this array is stored. So if I copy that down to my commands box, I'm going to say print, right? This executes and gives me those 3, right? So I don't know, maybe we can say like orig equals copy.deep copy, because we always copy everything. And then like, I don't know, average is equal to np.average of average. And put that into an array where we have average times 3 or something. So now I went through and it took the average of each one, right? And it put that here as my average shift. So if I shift this now, it's using the data that's stored in the tree, not the data that it calculated. And so it will do that all by some average amount. And there's lots, I mean, you can do stuff like this throughout OMFIT profiles, right? Because you should really think of OMFIT profiles as like a Python class with scripts that help you interact with stuff. And you're still the physicist in control of what's going on. Cool. All right. So there's some other tabs that we didn't talk about, or I guess any other questions? Yeah, Jeff.
I assume all the fits are completely independent. There's no way to like have your TE fit formed by your TI fit at all.
Not automatically. Sometimes this might be a good idea, right? Like if you want to potentially use a ratio of your TI and TE profiles to fit like TI in the edge where we know it's hard to get TI. You can do that through manual iteration. See, Quinn maybe knows more than I do here.
I was just gonna say the way I would do something like that is if you pick one of the spline options, right, you can manually enter the not locations. So that's kind of like you're obviously injecting bias, but there you're like having all of your fits use the same knotted locations.
Yeah.
So, and there's actually a way to do that on the fit. You can do one fit and do your spline, and then hit the button that says like copy these fit settings to all fits.
Yeah. So this copy thing is it's available for all the types of fits, not just TA spline. But if you like something, right, you can copy it to all fits. That gives you the same settings everywhere.
Yeah.
It doesn't necessarily allow you to talk between like a TI-TE ratio, but it does give you the same settings. Yeah, but I mean, you can manually edit it to get the TI-TE ratio. That's basically it. Cool. Any other questions about what we've talked about so far? Sweet. Okay, so on to the other tabs. There are fetch, filter, slice, export, and compare that we haven't talked about. I think we'll do these in order now that we've talked about like the main oomph of the fitting profiles. So fetch is pretty obvious. Get your data, right? We talked about equilibriums. Everything I did today was just on OMFIT 01, which is your standard magnetics only on D3D. You can see for this shot, there are lots of different options. I worked on the shot a lot, and so there's lots of different equilibrium options. Many shots will have different equilibrium options. And we'll talk a lot about this in 2 weeks, but you want to have your best equilibrium for your best fits. So just choose wisely there. There are also settings for Thompson, if you'd like to disable a letter, or sorry, a laser or not, or move the data already to master separatrix early on. There are options for CER. This is basically letting you choose from different workflows of the process CER. Best is in order of qualities, SIR-FIT, LSIR auto, LSIR quick. SIR-FIT is manual, SIR auto is a more extensive analysis, and SIR quick is really fast, right? This will automatically just choose the best one available. But if you have one that you particularly like, you can set it to it here. Sometimes also CER will not just be measuring carbon. It will be measuring some other element, right? And so you can allow for those lines by editing this text. If you want to do this, you should talk to the CER group again. Using diagnostic data involves talking to diagnosticians, so please go do that. And then there's some advanced CER settings too, which I won't even bother to touch. There are a bunch of different diagnostics that aren't automatically fit or automatically gathered. So for example, you might be saying, okay, well, ECE also measures the electrode temperature. Why aren't we using that in our fits? Well, you can. Press this button to load it into your workflow. Same thing for a bunch of other stuff. I'm lazy and know this module well, so sometimes I just use this module to load the data. And so if we go back to this thing, I might just deselect all these modes and just run the fetch mode, just fetch the data, and then operate from the data that's saved in the tree. Yeah, I mean, typically you eventually fit it anyway, because that's the point. Fetch, yeah, I think it's pretty straightforward. I don't know if there's other, oh, I guess occasionally for hydrogen experiments, instead of deuterium experiments, you'll want to change this working gas to whatever it is. And then you can also add supplemental data from another shot in time, which gets loaded in if, for example, we have this issue in our case now where I didn't have any core CR data, right? If I have another shot that I trust the core CR and I trust it to be very similar, maybe I could load it in from there and then move over, right? So this gives you just a little flexibility to do that.
Oh, when you were fetching the, for equilibrium settings, EFIT tree, I don't understand why, I mean, you're showing us kinetic profiles. What is the point of having an EFIT 01 there? Because the kinetic profiles never feed back into EFIT 01.
Correct, yeah. So with this workflow as it is, you're just fitting profiles onto an equilibrium. That's it. In the process of making a kinetic equilibrium, so like through workflows like we'll talk about in 2 weeks, or with Cake or with any other tool, what you do is you have a base equilibrium, then you fit the profiles, then you map the profiles onto the equilibrium, you resolve the equilibrium with the internal profiles, you get a slightly different mapping, you do it again, you iterate back and forth until you have something that agrees well. So maybe that was already done in this case here, right? This Cake case or this manual kinetic EFIT time case, right? These are all generated by different users. And so who knows what they did? Maybe you did it and you trust it. Maybe a friend did it and you trust it. Maybe it's something completely random and it has really bad fits in the profile.
You just need flux surfaces basically to be able to do the mapping from the
You
diagram.
just need the flux surfaces, yeah.
Thank you.
Cool. Sweet. The filter tab is really interesting. This is a whole another layer of flexibility in your shots. There are some pretty obvious filters here. There's elm selection and rejection. By default, it's just 0 to 1 of your elm phase, which means all the data in your shot that is not elming. I think if we press the question mark here, yeah, so this defines your elm phase, which is a standard OMFIT convention. Anything during an elm will be negative. -1 is the start of the elm. The end of the elm is 0, and anything from 0 to 1 is data that's not elming, right? So this is just throwing out stuff that's exactly happening during elms. And there's a whole elm filtering module, which I believe is, it's also available by import if you want to go check it out, and it's a whole nother tutorial there. But this will let you filter around that. Why might I want to do this? We'll say I'm interested in getting a shot, right, that has really fast elms, and I just want to know what like the maximum pedestals are. I can go to my accepted time interval and I can say, okay, let's accept everything. I mean, okay, let's just do it. Now we're doing like really single time slice analysis here. But let's go to, let's accept everything from 2000 to 4000 seconds, right? And then if I go to the slice tab, right now it's just set for 20 millisecond handing windows. We can change this to a boxcar window to equally weight everything. So assuming this is like a stationary discharge, right? And we can put this up at like a 2000 millisecond window. Now we have a ton of data. In this discharge, there's a lot of elms, right? So maybe we don't want the whole evolution of the profile as the elms crash and rise. So then I can go to accepted elm phase and just choose like the last 80% or something, right? And so I'm only choosing the very end of the inter-elm period, or some other iteration of all this, right? And so this lets you filter your data based on events that happen in the plasma, which is really, really powerful, and you can do a lot with this. Similar sort of thing exists for sawteeth. And then there's this interesting button up here called event synchronization, which is very cool in that it lets you do some neat things. So typically it's with respect to an elm or a sawtooth, you can synchronize your data and put it all on a new time base so that you're all in one space. It also has a manual option. And the manual option basically does something that I've done with manual time selection manually in the past. But it lets you put in events of when stuff happens. And then these will be my new way to synchronize the data across those events. So say I have things like this. What might such an event be? Well, in this particular discharge that we're looking at, you didn't know this, but this has big spikes in the vertical position. right? Which are not captured in your Elm filter. They're not captured in your Sawtooth filter. You wouldn't know about this if you're only looking at the profile modules. But this is obviously, I think this is your positioning your Z-axis. These are some events that we should take into account when we're analyzing this discharge, right? So this event synchronization thing, or these manual time filters and careful application of this would let me say, like, select all the data that's only here or here, you know, and synchronize my analysis to these external events that are happening in the discharge. So this sort of like implementing other constraints into your workflow is very much possible in OMFIT profiles already, and supported by a bunch of these tools. It's very flexible, so free to explore as you wish, basically. Those are these tabs. Slice is pretty obvious. I guess there's a couple other things we didn't talk about. There's spatial averaging, which is only useful in very specific cases where you're like moving your plasma back and forth to get better resolution with the diagnostic. You can tell it when you're doing that and try to account for it that way. I've lost my GUI. No. Get it back up. And then there's also options to interpolate in time where data is missing. So for example, if I had missing CR data in the middle of the shot, but I trust earlier in the shot instead of a different shot, I can interpolate forward. As you saw with these profiles, if I did that in this shot, it would be bad because early in the shot when I have data, the CR core is really low, right? And then later in the shot where I don't, the temperature is obviously higher. It's not always useful. And you can make your windows casual if you're trying to do time-dependent events. And then there's some diagnostic specific stuff as well. The last two things we didn't talk about are export and compare. These are exactly what you think and pretty straightforward. You can export the profiles that you generate into lots of different formats for compatibility with other OMFIT modules and more advanced workflows. You can make P files with the press of a button and then send those off to core transport or whatever needs it, right? You can export to MDS Plus if you want to for various reasons and add a comment. You can export to U files so that you can run these in trans. We'll talk about that in 4 weeks. And then compare is just compared to some other types of profile fitting, right? If you do profile fitting with two tools and they're different tools and different workflows and you end up with the same profile, that's pretty good. We like that. It's pretty trusty. So yeah, those were most of what I had. If there's any questions, let me know.
All right, so for those of you who have been plagued by this bug, there is a solution, and we'll put it in the chat.
Yep.
And as well, he's going to send an email to the OMFIT users email list to let you know what that fix is. It's on the no machine side. It's not an OMFIT problem per se, except that OMFIT uses TK.
Love no machine.
Yes, it's great when it works. Were there other questions?
Didn't see anything.
All right. Well, thanks, Oak.
Yeah.
You did great.